Well, all right, our next talk is given to us by Warren McGovern. He'll tell you it's joint work with other people, and the title is Algebraic Frames and Minimal Primes.
Thank you, Chip. Thank you, Jim, as well, for having us here and organizing this. I have been one who has been not traveling due to COVID, which is insane that it's been 4 years. But just the past 6 months, I've made a decision to start to come out. So this is perfect timing. I made it to Bolivia. Brian had me up to New York recently, so I'm really excited to get back into traveling and seeing everybody here and meeting some new people. So let's get into it. I'll be talking about algebraic frames and minimal primes. And so this is a little bit of a piggyback on what Ramiro did and what Papiya did. And I need to point out this is joint work with the doctors Bhattacharjee and Madinya, Albert here. So a lot of this is the ideas are stemming from Albert's dissertation. Papiya gave a talk on algebraic frames, not necessarily compact. So the top need not be compact. So this is a generalization of the coherent frames, which come up as, you know, the frame of radical ideals of a community to bring with identity. It is a generalization of the frame of convex L subgroups of a lattice ordered group, which need not have a top element being compact. And as we know, and we learned here, I think in 2019 with a talk by Friedrich Werung, that not every algebraic frame with FIP is actually one of those two. So this is even more general than those two situations. And so Papiya mentioned that Albert in his dissertation was working on trying to generalize some of the theorems from frames with FIP. Now is a good time to remind you, if you don't know, FIP we've learned because we wrote a paper recently and somebody pointed it out to us. These are also sometimes known as arithmetic lattices. And they have multiplicative lattices. There's other names for them, but we like the FIP. That goes back at least 50 years. So we're good with FIP. That means FIP means the finite meet of the two meet of compacts is again compact. So when that happens, you get the lemma on ultrafilters, you get a bunch of things going on, and then you start using those tools to create things. And this is a lot of work from Martinez and Zenk and Papiya. And so Albert's dissertation was sort of like, how much of that generalizes? Let's get rid of FIP and see what happens. And so I'm not giving a talk on Albert's dissertation. I encourage you to get a copy of it and look at it. And it lines up the theorems that work. So a lot of those theorems end up being if and not only ifs. Things end up being this implies that, then this one. So there's different classes of algebraic frames that are taking place in here. So I will mention the CAB, the CAB minimal primes, and let's see if I hit an arrow and that works. Nope, how about a space bar?
You have to go back to the screen again, that's what happened to me.
Okay, so we know what a frame is, pseudo complement, so hopefully by now we know compact elements. Algebraic says every element is a join of compacts. Throughout this, I'm not assuming FIP, okay? So Albert came up with a nice name called subcompacts. A subcompact is a finite meet of compacts. And if you take the collection of subcompacts, that ends up being a lattice. So you can do things on the collection, you know, form ideals of subcompacts and get bigger frames that this algebraic frame will embed into a frame with FIP. So lots of stuff, really stuff. I'm not talking about those kind of things. Finite intersection property. Here's the nice example is the collection of all convex L subgroups of a given lattice ordered group. For those of you that don't know, I am a student of Jorge Martinez, who was a student of Paulo Conrad. And so my expertise comes from the theory of lattice ordered groups. And so, and in fact, I should admit, because I was looking around and I see non-abelian lattice ordered groupers in here. I feel much more comfortable in the abelian lattice ordered groups and W objects, Archimedean L groups and stuff. So, but I dabble in rings, and a little shout out to a co-author of mine there in the Zoom, Ibrahim. It's good to see you. I'm waving. Yeah, hopefully here's me. So we know what the element definition of prime is. Spec is the collection of the prime elements. And as Papiya pointed out, so I didn't get a copy of her talk ahead of time. So a lot of doubling on here. So he did a lot with D elements. And so I think Papiya's idea, maybe with future students as well, and Albert is to. Albert has pushed an understanding of where the theorems are and what implies what and what you need to get stuff, but they haven't gotten to the D elements and how to generalize the Martinez-Zenk stuff without FIP. And so I think there's some ideas there. Here are some things in Dr. Madinya's, he looked at several statements, and here are some of the several statements. I'm not gonna put them exactly, but these are sort of, this is FIP, and what you get ultrafilters on the compacts. That's the lemma on ultrafilters. You get something as minimal prime, if and only if each compact below it, then its C perp is not less than or equal to it. For those of you that study commutative rings with identity, here we would be more in the class of reduced rings, so no nilpotent elements. And then there one of the ideas in semi-prime rings, commutative semi-prime rings, is that minimal primes are the primes that precisely have this property, that if you take an element below the prime, then there is some element not below the prime that annihilates it, and so multiplies times 0. So this is more of a frame theoretic thing than just commutative rings. That should say finer. And Papiya probably pointed this out, the whole kernel topology on min of L is finer than the inverse topology on min of L. Again, here the whole kernel is the U of compact, and then the inverse is the V of the compacts. And so when you have FIP, that whole kernel topology is actually finer than the inverse topology. That theorem does not hold in general. That's one of the consequences of his dissertation, is that there are examples. And in fact, there's a characterization of when that happens, and that has to do with the cab property. So min of L is always zero-dimensional Hausdorff, min of L inverse is compact T1. Each minimal prime is a D element. These are all consequences. And so just asking questions about these without FIP, right, gets you dissertation. So, and a good one too, in my opinion. So, this better than I can hear. Perfect. I wrote that just to make sure that I didn't forget to say that. So, so we set out to find some concrete examples of algebraic frames without FIP that could show the difference between these classes. That's what we were sort of interested. We have these theorems. This implies this, right? Do we have a counterexample? This implies this. Do we have a counterexample? And so we were trying to find some examples, like concrete examples of frames that would do this. And so here is one example. This was our first example of a frame that does not have FIP. Okay. Notice, so what we're doing is we're taking 0, 1, 2, we're taking all the naturals, and then we're putting a top element, right? And so this is an algebraic frame, and in fact, every element is compact except for omega here. It's not compact, it's a join of stuff. A is compact, B is compact, you meet A and B, and the meet is not compact, so it doesn't have FIP. However, in studying the minimal prime space of this, I'm pointing and the people there are, I should be over this, right? Wait, I should be over here, right? And if I can point, no, that doesn't. So, right, there's your minimal prime, and it's an isolated point. It's one point. So this is trivially, whatever you want to talk about is going to be trivial, right, for here. So, and we figured out we could always add on this diamond. You take an algebraic frame, you add on the diamond on the top, and you get another algebraic frame without FIP. But we're sort of like this is sort of cheating. We're just, it has to find stuff. Algebraic frames where the minimal primes started to get dicey and started to get weird. Okay.
I didn't succeed. I was gonna make it follow.
No, I didn't want to follow. Okay. All right, so here is one of the central definitions of his dissertation. So a prime element is said to satisfy the cab property. And what does that mean? Compact absolute property or something? That's the dissertation meaning. If we take a prime and we take F star of P is the set of compacts, so that C is not less than or equal to P, and then P is the join of those C perps. For those of you who know that lattice ordered proofs, this is right. This is Conrad's theorem on characterizing the minimal primes of there he did it more in the positive cone, and he took ultrafilters on the positive cone and stuff. And then Martinez, this Papiya mentioned this, Conrad and Martinez in 1973 or something generalized to lattices, Browerian lattices, which we now know are the algebraic frames. algebraic Brownian lattices, okay? And so cab of L be the set of prime cab elements, and then in his dissertation, he gets that all of these are actually minimal primes. If L has FIP, then cab of L equals min of L. The converse of that statement is not true. You can have cab of L equal min of L and it not have FIP. Obviously, a simple example would be the diamond that we just did. Okay, but we wanted more weird, interesting examples besides that sort of cheating. So, all right. So this is actually a talk about, and normally I would say this is a talk about lattice ordered groups, but it's not. This is a talk about Hahn groups that are not necessarily lattice ordered. So, and I feel I got excited about this because I felt like I was playing with tools in the, you know, that were used to be heroes of mine and gods to me. And so the Conrad-Harvey-Holland theorem, you know, just dealing with these Hahn groups. And so I had to learn about Hahn groups that weren't necessarily lattice ordered groups. So that was sort of interesting too. Now, in the end, I've written up V here, but I'm going to cheat. I'm not going to deal with V because V is too hard. Okay. So, and I'm going to do this with the integers. You can do this with the reals. The Conrad-Harvey-Holland theorem has to do this over the reals. You take functions from a partially ordered set gamma, okay, into, you can do it over the reals. I just made it for simplicity. I did it. You can do this into any subgroup of the reals. I did it into the integers, okay? And F satisfies the ACC on its cozero set. The cozero set is the set of things in gamma which don't go to zero, okay? And you got to satisfy the ascending chain condition on that, in which case you get maximal elements in the cozero set, and then that you use that to define positivity, okay? So to each F we can associate, because of the ACC, you get every element in the cozero set lies beneath the maximal element. So you can take the maximal element in the cozero set. Gamma might not have maximal elements, but you're looking at ones whose cozero sets have maximal. And you can't just do maximal elements. You got to have the ACC, because if you just do maximal elements, you can really screw it up and not get a group. So this is the Hahn group. You then partial order the Hahn group by setting an element to be positive. If you're positive on the maximal elements. So for those of you that, if this is lexicographic extension, so you know, if you think of R cross R lexicographically ordered, that would be two copies. And you put one on top of the other. And so something's positive if it's positive in the first coordinate. Okay, so this actually gets really hard, so we don't deal with that. We deal with the restricted Hahn group, which is so much more easier. These are the functions that have finite cozero sets, which automatically have ACC. And so now I'm just dealing with finite cozero sets, and I can look at just a finite number of maximal elements, and I'm positive there. Okay. Now's maybe a good time to, I think, let's see. Oh, I should remind you this. This is a classic result about when the Hahn group is an L group. And it turns out it's an L group if and only if the partially ordered set is a root system. To remind you what a root system is, that's if you take an element in the partially ordered set and you look at the things above it, that's a chain. That's what a root system is. And so if this is an L group, then gamma is a root system and conversely. And sigma just happens to come along for the ride because it's a sub L group in there. In that case, it's a subgroup. So this is the classic result. And then in the 60s and in the 70s, when people were studying Hahn groups, you know, they would assume you had a root system. Their theorem, the Conrad-Harvey-Holland theorem, was an embedding of an abelian L group into one of these, and they took gamma to be the root system of values. And the values in an L group form a root system. And so this was a nice, huge theorem, the Conrad-Harvey-Holland theorem. So there it is. You can embed G into one of these. This is for the abelian L groups, of course. All right. So L groups, their convex L subgroups, have FIP. So we can't, if we're looking for weird examples of things that don't have FIP, we can't use L groups, but we can use Hahn groups that are not over root systems, okay? So the objects of study, Reese groups, so around Conrad was at Tulane, down the road, I guess, in the 60s, and so was Fuchs. Laszlo Fuchs was there around the same time, and Clifford, and people doing semi-group theory and stuff, and Fuchs has a paper on Reese groups. And he looks at what these Reese groups, these are groups that are partially ordered that have the Reese interpolation property or the Reese decomposition property equivalently. And he has a nice paper and he studied the O ideals. Rachunik in the early 1970s, I think 1973, showed that these O ideals actually, so these are O ideal. An O ideal is a convex directed. Directed meaning take two elements in the subgroup, there's something above it that's in the subgroup. Okay. And so in particular, you can take 0 and an element in it, and you get a positive element that's bigger than in there. So these are the O ideals, convex O ideals in an L group are the convex L subgroups. So they showed that these are, in fact, all you have to deal with is the positive cone. This is a standard result for L groups. You just, hey, without loss of generality, we assume we're positive, right? That comes up here. And so the same thing goes here. These are nowadays referred to as faces, these convex directed sub-semigroups of G of the positive cone. And they're an algebraic frame. These are all algebraic frames. Ken Gooderl, who's a ring theorist but does some C-star algebra stuff, has a book called Partially Ordered Groups with Reese Interpolation, something like that. And Reese groups are more general. If you assume that the Reese groups are isolated or semi-closed, that's this property, then these are what are known as dimension groups. And this is, a lot of people are studying dimension groups. And so L groups are dimension groups because they have the Reese decomposition property. And so, but these are much more general. Conrad had a student named Teller. I'm not there yet, so maybe a little bit of history. Conrad had a student named Teller, and they studied some Hahn groups without it being a root system, and showed they came up with the name of pseudo lattice ordered group. This had to do with values. You had enough values, which were maximal, maximal O ideals not containing the element, but you had enough of those to differentiate between the convex O ideals generated by positive elements. He called them pseudo lattice ordered groups, and Teller showed that every Hahn group is a pseudo lattice ordered group. And then years later, they showed that pseudo lattice, or maybe a few years later, they showed that pseudo lattice ordered groups are actually dimension groups. So there's this class going lattice ordered groups, then pseudo lattice ordered groups, dimension groups, and then Reese groups is the biggest one. So there's this sort of filtering in there. So in the end, I'm just dealing with the restricted Hahn group, which is an example of a pseudo lattice ordered group. Okay. And so what it got me thinking, I wanted to learn about those. Let me give you an example, just to sort of put you some easy 2 examples. Let's see if I can get this right. All right, so I'm going to take a real nice, easy, partially ordered set. There's your partially ordered set, and I hope you get the idea that A here and B here and C, right? So we take 3 copies of the integers and we Lex extend Z cross Z above Z. Think about it that way, not an L group, right? Because to be an L group, you have to Lex a totally ordered thing on the top, okay? Not a root system. I got one element that's beneath 2 things, the things above it. So if I take sigma of this thing, it is not an L group. And sorry about my mouse writing. Not L group, right? But it is a nice little group, okay? It's easy to look at its frame of O ideals, and its frame of O ideals will actually have the FIP. Shoot. Okay, so too simple, but we can make that, we can make this a little bit harder. You all get the idea here? Take 2 points above an infinite number of an anti-chain. Take the restricted Hahn group over that, and then it turns out that will give you an algebraic frame of O ideals, which doesn't have the FIP. Okay, and so I'm not going to give you all the details, but the details get into looking at co-zero sets. Guess what? I study C of X, and so I feel very easy around studying co-zero sets and 0 sets. Make everything, we actually positive just says you're positive at the top. I don't even feel good about that. I got to make them positive everywhere. So we call them firmly positive because strongly positive means something in other places. So we came up with, and maybe the referee, we haven't submitted this yet, so. But maybe firmly positive in these Hahn groups would mean it's positive at every place. Well, if you take an element that's positive, you can take its absolute value, right? Just make it positive at each of those points, and they will generate the same face. They will generate the same convex O ideal, the same O ideal. So there's a lot of details that are going into the theorems here. I'm just sort of giving you the end here. So what ends up happening in the restricted Hahn group, and then I'll tell you why it's not good in the Hahn group, okay? To each S here, we take chi of S as the characteristic function. Remember, these are functions from the partially ordered set into the integers of the reals. So I can talk about characteristic functions, okay? If I take a finite set, then I get an element in the restricted Hahn group. So I'm 0 everywhere except for a finite number of points, and I'm 1, okay? On that set. Now that set might be an anti-chain, it might be, right? In the end, it only matters what I'm doing at the maximal elements. And so the maximal elements end up being a trivially ordered subset. So in fact, there's a 1-to-1 correspondence between the finite trivially ordered subsets of gamma and the compact faces. So these are the compact elements of the frame. So we can characterize in the restricted Hahn group the compact elements in this frame. They're the ones I take a finite trivially ordered set, and I take the characteristic function by that. That'll give me the best possible thing. Think about the Hahn group. Now you can do an infinite trivially ordered set, and that will live in the Hahn group. And on that, I can take the characteristic function, but I can also take the function that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as I go along. Those will have the same maximal elements, but will generate 2 different O ideals, right? One's going to be infinitesimally larger than, right? Maybe not infinitesimally larger, but this is, right? They will not generate the same subgroup. So in the Hahn group, it gets to be, here it's nice and easy, it's finite. So if I'm, whatever I do finite here and I do finite here, eventually I'll generate the same, right? They'll be Archimedean equivalent, okay? All right, so what's useful here is if you take 2 elements, we look at the lower bounds of alpha and beta, might be empty. If I take 2 discrete things with nothing below it, that could be empty, okay? So the frame of faces of sigma has FIP if and only if for each pair. Take the lower bounds and then take the maximal elements of the lower bounds. Could be empty. Okay, but it's a set. Covers means take any lower bound, it's beneath one of the maximal ones. And the maximal ones have to be finite. So that example before that I gave with the with this one down here, right? Take these 2 elements, the lower bounds are all of these, not finite. So, right, the O ideal, the intersection of the faces generated by these 2 things will be the subgroup that's generated by all of these, which is not compact. And so you got to have a finite number of maximal elements to get FIP. So here's an example, which is not a root system. All right, then I just did that. Those are the 2 we gave you. All right, so the co-0 set, the 0 set. All right, so now we're trying to understand the minimal primes. Right, now we have this restricted Hahn group. I look at trivially ordered sets. I know what the compact elements are. Now I'm trying to understand what the prime faces are, or the prime elements of the prime O ideals. First of all, in L groups, prime means A inf B equaling 0, then either A is in it or B is in it, right? But we don't have least upper bounds because we're not an L group. So we have to go back to the official definition of intersection. If the intersection of an O ideal intersect another O ideal is beneath the O ideal, I think I wrote this somewhere. Yeah, there we go. Right, so an O ideal is prime if for any 2 ideals J and K. If the intersection is there, then one of them is in there. Because that's now, right, the infimum, finite infimum in the O ideals is the intersection. So this is the translating the definition on the frame of faces over to the O ideals. So it's nothing to do with A inf B, right? We don't have least upper bounds and stuff like that. All right, so we've got this gamma out there. This is the typical thing that we do, right? In C of X and in W, we take its co-0 set, okay? The co-zero set of an O ideal is the set of alphas so that this is basically the union of the co-zero sets of the elements from I, right? So f of alpha is not zero, the zero set is the complement of that. For any of O ideal, cos of I is a down set. So if you take anything below it, because of convexity, the characteristic function on that singleton set will also be in there, and now I'm there. So, and then of course, it's a complement. The zero set is an upset, okay? And so we're trying to understand prime ideals. So we now have to look at filters on a partially ordered set, and you're probably thinking, wait a second, this isn't a lattice. So we have to be very careful with how we define a filter, and this is our definition of how we define a filter. What does it mean? It's obviously an upset, right? This is just a partially ordered set, but a filter says, take two elements in there, and there is a lower bound of it that's in there. Not all the lower bounds. That's too much. We just need existence of at least one. So we can get lots of filters depending on all different kinds of lower bounds, okay? A maximal filter is called an ultrafilter, and the set of ultrafilters of gamma is denoted by ultrafilters of gamma. We do not assume that these ultrafilters are proper, meaning gamma itself might be the ultrafilter. But if you think about that, that means gamma has to be a downward directed set. Take two elements in gamma, right? For gamma itself to be a filter, that means there's a least upper bound in there that's also in there, so I'm downward directed. Conversely, if I'm downward directed, gamma is a filter. So if you're not downward directed, you take a partially ordered set that's not downward directed, then these ultrafilters will automatically be proper. They won't be the whole thing, okay? There's a reason for this. It'll come up. I hope I remember, okay? So it turns out an O ideal is prime if and only if its zero set is a filter on gamma. Okay, so I don't know if you've caught this, but basically what we've done is we've created some nice pseudo lattice ordered group that has an algebraic frame of O ideals, and we've turned this into a question of partially ordered sets and ultrafilters on partially ordered sets. I don't know if that's easier. I'm not convinced that this is actually easier, but it has been fun playing around with partially ordered sets and trying to how to create partially ordered sets. Okay, so let's see, what do I got? All right, so I want to give you a correspondence, right? We take a prime O ideal, we look at its zero set, I get a filter. Okay, again, this sum. Its elements are finitely non-zero, so I can literally track it back to the filter. If I did this on the Hahn group, all bets are off. It would be infinite kind of, MF would have to be infinite, and it's much harder. What we did find is that there's a student of Conrad, Anderson, Marlowe Anderson, and he wrote a paper with, I want to say Kenny. Yeah. They wrote a paper and they characterized the minimal primes of a Hahn group over a root system. And it's really interesting. They take these admissible filters of elements of trivially ordered sets. It's really cool. We haven't gotten to that point. We haven't gotten to the Hahn group, the general Hahn group in characterizing stuff here. It seems really hard, but maybe not. Maybe there's hope there, but this is all on the restricted because we can literally take a finite number of elements and look at an element over here in the restricted, take an element, I get a finite set, a co-zero set. Okay, so we take a prime O ideal, we get a filter. Now let's start with a filter in gamma. We take the set of F whose co-zero sets are disjoint. So set theoretic disjoint from the filter. And it turns out that you can show that this is the set of all F. This ends up being an O ideal of the frame, and it ends up being prime. And the zero set of this object is the filter. So there is a nice by one-to-one order preserving corresponding between the filters of P. That should be order reversing. Ooh, typo. So can I strike out here? This should be order reversing correspondence. Because the bigger the filter, the smaller this gets. Yeah, this should be reversing. is a one-to-one order reversing correspondence between the filters of, and that should be gamma, and prime faces of sigma. Okay, and so then what do we get? There's a one-to-one correspondence between the ultra, and that should be gamma, ultrafilters of gamma and the minimal primes. So the minimal primes of the restricted Hahn group correspond to the ultrafilters. Okay, by the way, in case you're curious, maybe now's a good time to see if I can do this. Nope, but I can. Let's see. Not a root system, so by this I mean I'm all right. The two top elements are bigger than the two bottom elements. Just a simple example here, not a root system. Its algebraic frame would have FIP because everything's finite here. Okay, so I'm Lex extending a copy of Z cross Z on top of a copy of Z cross Z is what we're doing here. Not an L group, but a pseudo lattice order group. What would be the ultrafilters? There's going to be two of them. It's going to be the principal filter generated by this element and the principal filter generated by this element. And so then that'll correspond to two minimal primes in the restricted Hahn group. Okay, and so what if we right? What if we just made it easier? Now you're like, there's no filter going on in there. Trivially, there is. The singleton set would be an ultrafilter. The singleton set would be an ultrafilter. The singleton set would be an ultrafilter. So these are just, you know, you gotta keep an eye. It's weird. So you don't have to have things below it, right? And in some sense, there is no ultrafilter that contains two distinct points because they don't have a lower bound. So there's no filter that contains. So what do I got? Like 8 minutes? Right, that's good. So this was, remember I said that gamma is a downward directed set if and only if gamma itself is an ultrafilter. Well, if it's an ultrafilter, then I look at its corresponding prime, right? And that's just 0. So 0 ends up being the minimal prime, in which case in the context of Albert's dissertation, this is trivial. It's the minimal primes of one element. So we really don't want the partially ordered set to be a lattice. We don't want it to be, you know, a downward directed set because then you're just dealing with one minimal prime. Okay. So we take an ultrafilter and we take P sub U, right? These are the functions whose elements, the co-zero set of those are set theoretic disjoint from U, its corresponding minimal prime, I have no idea. Okay, most of us who have experience dealing with ultrafilters know this property about ultrafilters on sets, okay, like or zero sets or something. You take an element not in the ultrafilter and you can find an element in the ultrafilter which is disjoint from it. That's too strong. We have lattices going on there, and then we're dealing with proper filters and ultrafilters. So that property ends up being exactly the cab property. That's what this is saying. PU is an element of cab of L, and it's one of these nice minimal primes that are the union of the C perps, so that C is not less than or equal to the prime. One of those, if and only if it's cab, if and only if for every alpha not in the filter, there is some beta so that they have no lower bound. In general, on partially ordered sets, you can have ultrafilters that don't have this property. And that's what we were sort of looking for. And so, let's see what else I got. Oh, an example of an algebraic frame for which cab is, right. So take your favorite frame, put a diamond on top of it. You change nothing about min of L. And all of min of L, if it was an algebraic frame with FIP to begin with, then cab of L is min of L. They all have the nice little properties on the minimal primes. We put a diamond on top. We don't change that. Nothing is being changed there. So we want an example where cab of L is strictly smaller than min of L. And so I'm going to draw a little picture, and I hope I do this right. So I'm going to take I'm gonna take a countable anti-chain, and we're gonna call these x1, x2, and so on. Okay, you get the idea there? And then over here, I'm gonna take a chain that goes down to also countable. Okay? And then I'm gonna take one element A here. Now, what is the order? I'm gonna draw the picture to make it look like this. X1 is less than or equal to Y1. A is greater than or equal to all of the Xi's. So A is greater than all the Xi's. And incomparable to all the Yi's. Okay, so we know that we have these things, they're not really getting closer in any kind of considerable sense here, okay? X2 is less than or equal to Y2, and therefore it's also less than or equal to Y1. Because Y2 is less than or equal to 1 and it's a partial order. X3 is less than or equal to Y3 and therefore Y2 and so on. So I hope you all get the idea here. And so on. Okay, so what are the ultrafilters? Well, the ultrafilters are going to be the principal filters generated by the Xi's. That's not a singleton set, right? It'll contain X1. The principal filter generated by X1 will contain X1 and Y1 and A. The principal filter, which is an ultrafilter generated by X2, will be X2, Y2, Y1, and A. Xn will be Xn, Yn, Yn minus 1, Yn minus 2, Yn minus 3, all the way up, and A. So we're gonna get ultrafilters all containing those. And we're gonna get this as an ultrafilter. Right, the ultrafilter that contains all the Yi's. That's a filter, that's right. Once I contain one of the other ones, then I go far enough down in here. Any ultrafilter that contain this and any of the Xi's, say it contain Xn, then look at Xn and Yn plus 1. They have no lower bound, can't be a filter. So that's an ultrafilter. Okay, now look at A. A is not in the ultrafilter Y1, that special chained ultrafilter, right? Is there any element in this ultrafilter that doesn't have a lower bound with A? No. Because if I take any element, Yn, Xn will be a lower bound of Yn and A. So this ultrafilter doesn't satisfy CAB. Meaning I have now the restricted Hahn group over this partially ordered set has an algebraic frame of O ideals in which min of L is strictly bigger than cab of L. All of these are principally generated, so they will have cab. So cab is all of min of L except for one point, that one ultrafilter. And so this was an interesting example that we were able to sort of come up with algebraic frames. Then after we did this, we found a paper by Mummert and Steffen that actually showed, was interested in looking at ultrafilter spaces on partially ordered sets and characterizing which kind of topological spaces could actually occur as ultrafilter spaces on a partially ordered set. They call them UF spaces or and there he has two examples. He shows that if you take any complete metric space, completely metrizable space, there you can create a partially ordered set so that the set of ultrafilters on that is homeomorphic to the space. And then showed that any locally compact Hausdorff space, you can put a partially ordered on the pre-compact open sets. You can put a partial order, you can create the partial order on those, and then the ultrafilters on that thing will be in one-to-one, it will be homeomorphic to the actual space. What's interesting in those examples is that if you don't have isolated points in your original topological space, then you have no cabs. Because we were always wondering, must cab be dense inside of min of L? The answer is no. You can have cab, so take your favorite take the Cantor space, or take 0, 1. 0, 1, there is a partially ordered space whose ultrafilter space, right, is this thing, and you end up having no cab. So cab can be actually empty. So it gets really crazy as far as the eye can see. So there's a lot of stuff in there. So I think I'm down to like 30 seconds. I'll leave you with some questions. One nice class that Albert was able to identify. So he comes up with a property that says cab of L equals min of L. That is a property on frames. Every prime, right, without assuming FIP. If you're FIP, then every minimal prime is cab prime. But what if you just have that? We have examples where that happens and we don't have FIP. So those exist. Okay, so that's a bigger class of frames. The question is, can we do D elements and D stuff? Can we generalize stuff from there? Because it seems to get to D elements, we need that. But what's really interesting is that property is equivalent to the statement, I'll get this right, that the whole kernel topology on min is finer than the inverse topology on min. So just those two statements are equivalent. In FIP, the whole kernel topology is always finer than the inverse topology. But that statement itself is equivalent to saying that min of L equals cab. If min of L inverse is compact, which always happens in FIP, then every minimal prime is cab. And at this point, we do not have a counterexample to that. So that's still an open question. This seems to be a smaller class in terms of, and maybe the restricted Hahn group can be used for that. Anyway, so I'm out of time. Thank you very much. We'll probably have some.
Groups is John and Holmes theory. Basically, groups come from this group.
Yeah.
The only example is we use that newcomer said somehow from ring theory. The same way. Oh, it's
The V, do you want the V or the sigma? I don't feel comfortable.
So just any single L group. Is there any ring theoretic construction?
I see what you're saying.
Any class of rings use these like L groups that can be like these rings.
So is this, let me rephrase and see if this is what you're asking. The Jaffardo and Kaplansky theorem says take any L group can be realized as the group of divisibility of a pseudodomain.
Yeah.
Is there some kind of theorem that says any pseudo lattice ordered group is
Name is the property that every ideal is generated by two elements, not
Okay.
elements.
so a two generated ring? Yeah.
Could this maybe produce such a pseudo L group?
So more a general question, like it's group of divisibility, right?
Yes.
So that would be a general question. Take a integral domain. When is its group of divisibility a pseudo lattice ordered group?
Okay, yeah, right.
No result. So it's left, and then Conrad must have just gotten other students and went in a different direction. So this line of pseudo lattice ordered groups has been taken up by others, but only in terms of the frame theoretic, but not the ring theoretic. But that's a fantastic question. That I've seen nothing about this. Usually ordered groupers stop and say it's not a root system, I'm out.
Yes,
So I think this is I think we can return to studying Hahn groups. I'm excited. Let's see if we can get something out of it. Yeah. That's a great question.
Well, you've got a remote question here.
Oh, yeah, sure. Let's see if I can move that down. Okay. For your research, from my understanding, is stated on page 7, 18, 19. Oh, I have, is sigma is prime if and only if, yes. J intersect K implies either J or K, yes. As you know, an ideal of commutative ring is strongly reducible. Every prime ideal, it is known that if I is semi-prime, okay, radical, right. Yeah, I would think so. In the sense, what do you think? Yeah, though I think when Abraham, thank you for the question and thank you. It's good to see you. Usually when people on the order side study the commutative rings, they assume that we're dealing with the radical ideals because that ends up being an algebraic frame. So it seems your question more goes into the lattice of ideals which might not be distributive. So maybe you're just asking that this O ideal is semi-prime in the sense of this strongly irreducible. So maybe maybe you're suggesting what we're calling prime in the sense of a frame in maybe in non-distributive lattices, they're calling strongly irreducible. So that might be related. So once I get away from distributive, I start to feel very uneasy. So I mean, I could always throw in arithmetic or something, right? If I'm an arithmetic ring, then the frame of the ideals form a distributive lattice, and then maybe that would be the more general, sort of like what Ramiro was doing, looking at the lattice of all ideals. So maybe, yeah, maybe there's something going on there. But again, when I lose the distributivity, I feel uneasy. I feel like I can deal with like modular lattices that are whatever crazy you want to do, right? On like vector spaces and taking their subspaces. So maybe somebody studied strongly irreducible in the context of arithmetical rings. Okay, I might, thank you. We might include that, look that up and maybe include that in our paper, so. Great. Any other? Thank you.
All right, thank you.